Okay, so we're going to talk about intercept less model. Okay, so what we generally have this kind of model, which is yi equals to beta 1 plus beta 2 xi plus ui. Okay, in intercept less model, your beta 1 is equal to 0. So what we have is, we have yi equals to beta 2 xi plus ui. We have this kind of model. So how do you estimate this model? Well, the estimated yi hat would be beta 2 hat xi. Okay, and you also know this, that yi, your actual yi's, is equal to estimated yi's plus error terms. This you know. Okay, so, and you can write your error terms as ui hat is equal to actual yi's minus estimated yi's. This is your error. Okay, and what you do in OLS is you take the square of these errors and you sum them together. So you take the sum of squares of these errors. Okay, so in place of yi hat, let me write this, which is beta 2 hat xi square. Okay, now I have this equation, which is summation of ui hat square is equal to summation of yi minus beta 2 hat xi square. Now what do I have to do with this? I have to find out the estimate for beta 2 hat, so I'll partially differentiate this. Summation of should be del of summation of ui hat square upon del beta 2 hat is, this 2 will come here to summation of yi minus beta 2 hat xi, and the coefficient with beta 2 hat is minus xi, is equal to 0. Okay, the term with beta 2 hat is minus xi. So since it is with equal to 0, so this 2 and this minus will go off, and you can simplify this term as summation of yi minus beta 2 hat xi into xi equals to 0. Okay, so because this 2 and this minus 1, when they'll go to the other side of 0, they'll be 0. Okay, so you can simplify this further to write it as summation of yi xi minus beta 2 hat xi square is equal to 0. Fine. So what do you have it here, which is summation of yi xi is equal to beta 2 hat summation xi square. Okay, this you have. So you can simplify this further to get beta 2 hat equals to summation of yi xi upon summation of xi square. Now note that these are not deviations from mean. These are not deviations from mean. So what are these? These are just your actual xi yi's. In general, if your model would have been yi equals to beta 1 plus beta 2 xi plus ui, supposedly if you have this model, then in that case your beta 2 hat, it could be written as summation of xi yi upon summation of xi square. Note that these are the lowercase letters and these are the uppercase letters. These show deviations from mean. These are deviations from mean. Clear? So you have this. So what you have to do is that you have to sort of remember this term, which is beta 2 hat is equal to summation of yixi upon summation of xi square. This is what you have to understand. Okay, now let us talk about how do you calculate variance for this beta 2 hat which you have, which is beta 2 hat is equal to summation of yixi upon summation of xi square. Fine. Now, so how do you go about it? Well, you have this beta 2 hat summation of, in place of yi, let me write the true model, which is beta 2 xi plus ui. This is the true model which you have upon summation of xi square, which you have. Clear? So you can write this as summation of beta 2 xi square plus ui xi upon summation of xi square. You can also write this as this beta 2 summation of xi square upon summation of xi square plus summation of xi ui upon summation of xi square. Clear? Now this will go off. So this could be simplified as beta 2 plus summation of xi ui upon summation of xi square. Supposedly if you have this you can write this as beta 2 hat minus beta 2 is equal to summation of xi ui upon summation of xi square. Now if I take the square for this, okay, and I take expectation of this, then this becomes the formula for the variance. So in this case, this is basically this. This is xi ui, that is I starting from 1 to n. So I can write this as x1 u1 plus x2 u2 and so on to xn un square, of course, upon summation of xi square square. This is what you have. Clear? This expectation is of course both on numerator and denominator. Well, if you expand it, what will you get is x1 square u1 square, x2 square u2 square, and so on to xn square un square plus 2 x1 u1 into x2 u2, okay, and plus so on to 2 xn minus 1 xn into un minus 1 un. Fine. All this divided by summation of xi square square, and you take the expectation of all this. Now the point is, you have to remember something. One, if you look at this kind of a term, which is your x1 square u1 square, let me just do it here as a working. If you look at this term, e of x1 square u1 square, how will you do? x1 square will come out of the expectation operator. Clear? Because this is x is non-stochastic. Because x is non-stochastic. And e of u square could be written as sigma square because of assumption of homoscedasticity, that is of equal variance. Clear? So all of these terms are basically your x1 square sigma square, x2 square sigma square, and so on. Also, if you look at this kind of a term, which is this term, so what is this? 2 of x1 x2 into u1 u2. If you have this kind of a term, so 2 of x1 x2 will come out of the expectation operator, being x1 and x2 both being non-stochastic, and eu1 u2 is like this. So this will be 2x1 x2 into 0. Why 0? Because of assumption of no autocorrelation. Okay, so all of such terms are basically 0. All of these terms are basically 0. And all of these terms are basically x1 square sigma square, x2 square sigma square, and so on to xn square sigma square, and all of these terms are 0. So what you can do is, when you take the expectation of all this, so this becomes sigma square into x1 square and plus so on to xn square. You've taken the sigma square common and plus 0 0 0, so that is all 0, upon summation of xi square xi square square. So there's no change in this because this is non-stochastic. So let me just put this here and let me put this in a different ink. So this becomes what? Sigma square. This becomes x1 square and so on plus so on to xn square as summation of xi square upon summation of xi square square. Okay, so this summation of xi square goes off with this square, so this becomes sigma square upon summation of xi square. Clear? So you have this. So variance of beta 2 hat is basically sigma square upon summation of xi square. This is what you have. Okay, and this sigma square basically this is the actual variance. It could be estimated as summation of ui hat square upon n minus 1. Okay, well, you have to remember this, that the kind of the model which we are running right now is yi equals to beta 2 xi plus ui. So how many parameters we have to estimate? Only one parameter, and that is why we have just lost 1 degree of freedom. In case of your actual simple regression model, when you have yi equals to beta 1 plus beta 2 xi plus ui, you have two parameters to estimate, which is beta 1 and beta 2. So you had n minus 2. Now you have just n minus 1. Okay. One important point is this. Now, there are two important results of this regression through origin model. So what we have analyzed till now is that in case of such kind of model where you have no intercept, this is your estimate of the slope parameter, and this is the variance of this parameter. Okay, and we have n minus 1 instead of n minus 2, okay, because we have just one parameter to be estimated. And apart from that, you have two other results which are important. Let me just do that in different recording. Okay, thanks.